Right, good morning or, evening, whatever. I'm going to try not to cough my way through this too much. And it's going to take me probably a little while to get back in the swing of things here, but we're starting. We technically started our kinetics unit in class today. We are just carrying on from there. So, what we talked about in class was the things that actually affect the rate of a reaction, the things that speed it up or slow it down, and that sort of thing. And so now we're going to talk a little bit more about how exactly we measure a reaction rate, because in chemistry, it's not good to just say, oh, that happened fast or that happened slow. We want to actually quantify that a little bit and have be able to talk about that using numerical values. So basically, the best way to measure the rate of a reaction is the change in concentration over time. As reactants disappear or as products appear, we can measure that change in concentration over time, and then we can sort of get an idea of how fast this reaction is moving. Okay, so in chemistry, and this is similar to physics in that a rate is usually a change in something over time. In physics, a lot of times it's change in distance over time, and that's going to give you a rate. Instead of distance in chemistry, we're going to talk about change in the number of moles of something or change in the concentration of something. Okay? And so our first hypothetical situation here, well, okay, and I guess you have this big part here to write. But basically, when you take your average rate, you're taking your change in number of moles of B over change in time, and another way of writing that is with the delta. Now, you could say change in number of moles of A also. That's kind of arbitrary that we picked B. It doesn't really matter because the concentration of A here should actually be decreasing, the concentration of B should be increasing. So, A reacts to form B. We're beginning with 1 mole of A. And so in this picture right here, in this first picture on the left, we've got all A. Okay, A is the red spheres. Now, you can't see that on your sheet, so I'm not sure why exactly I included this picture, because it's not helpful for you. Once you get to this middle one here, now you've got some red and some blue. So some of this A is being converted into B, and then by the end here, you've got, based on the stoichiometry in the equation, you should have equal amounts. Actually, no, I'm sorry. At the end of this thing, based on the stoichiometry, it should all be converted into B eventually. But, at 40 seconds, it hasn't all been converted yet. So, there's the way the reaction looks as it progresses throughout time. So notice the A is decreasing the red spheres and the B is increasing. And so here's some numbers to go with that. At time 0, there's 1 mole of A, and obviously there's no B. At 20, it should say seconds. Pretty sure it says seconds over here. Let me look. Oh, it doesn't say. Okay. So we will say 20 minutes here. I had seconds in my head for some reason. So 20 minutes and 40 minutes. There's 0.54 moles of A and 0.46 moles of B at 20 minutes, and then at 40 there's 0.30 and 0.70. So if we want to calculate the average rate here of this reaction, then all we have to know is the change in the moles of B and put that over the change in time. Okay. Now we could use, we could compare these two times, or we could compare these two times. Now, assuming that the rate stays fairly constant, those numbers should give you similar answers, but that may not always be the case. Sometimes a reaction, or oftentimes, a reaction slows down as it gets towards the end, and so the rate is actually going to change over time. But in this one, you can kind of pick whichever one you want. The one that would probably be best for giving the overall average rate would be using the 40 minutes and the 0 time. But here, just for the example, we're using 20 and 0. And that's going to end up giving you, at time 20, you've got 0.46 moles of B. At time 0, you have 0 moles of B. Okay? and you just take the 20 minutes minus 0 minutes, and that's going to give you 0.023 moles per minute as your rate. Okay, so all we're doing there is we're saying, all right, so at time 20, there's 0.46 moles of B, and at time 0, there's no B. There's 0 moles of B. Okay, so then we're just using that change in B over the change in time, and that's going to give us our rate. Could have done this, could have found the rate with respect to A as well. Okay, either way is fine. And this is kind of what I'm saying. Reaction of A to B, there are two ways of measuring that rate. One is how fast the products are appearing. The other is how fast the reactants are disappearing. And that actually is this second one here, speed at which the reactants disappear. That's the way you're typically going to see this measured for reaction rate. It's usually going to be the speed at which the reactants disappear. Okay? And so if we wanted to measure that, then we would take the negative of the change in the moles of A over change in time. Okay? And the reason for that is because we want a positive rate. And so if you measure the change in the moles of A, that should give you a negative number. So for example, if we go back over here, I had 1 mole of A to start with, and I had 0.54 moles after 20 minutes. So if I had measured this with respect to A, I would be taking 0.54 minus 1.00 over the time of 20 minutes. Okay, so that's going to give me a negative number, so that's why we put that negative in front, so that our rate ends up being a positive rate. Okay? Alright, so sample problem here. For the previous reaction example, calculate the average rate of disappearance of A over the time interval from 20 minutes to 40 minutes. So we have our data here, okay? And again, our rate is going to be equal to, here, it's the opposite of the change in moles of A over the change in time, okay? So we've got our negative here. At 40 minutes, there are 0.30 moles of A left, okay? So 0.30 moles minus, and at 20 minutes, there was 0.54 moles. We're going from 20 to 40 here. 0.54 moles of A left, okay? And then our change in time from 20 minutes to 40 minutes, I mean, that should be fairly obvious, but I'll write it down anyway. Okay. When we subtract those two and then divide them, get out my calculator here. Should give us our negative, no, not negative, because we've got our negative here. It should give us 0.012, and that's in, the rate here we're measuring is in moles per minute. Okay, you gotta pay attention to your units here. Moles per minute, okay? So that's the rate of disappearance of A in this reaction. Okay, so for this reaction, there are, oh wait, sorry, this is from the last, I think I messed that up on the notes, your note sheet too. Yeah, just cross out that change of rate with time thing. Cross out that first bullet because that's actually left over from the last heading. Most useful units for rates are to look at molarity. Okay, so we just did an example where we did moles per minute. Usually when we're doing this kind of reaction, we're doing it in a constant volume. The volume of the solution is not changing as the reaction occurs. So molarity and moles are actually directly proportional to one another. Okay, so for example, and we've talked about this, you know, with some other scenarios using the gas laws, where the coefficients in the balanced chemical equation can actually tell you something other than just a mole ratio. Here they're actually going to tell you a molarity ratio as well. Okay, so if this is a, you know, 1 to 1 to 1 to 1 relationship here, if you need 1 mole of each of those things in order for this reaction to occur, then it's also a 1 molar to 1 molar to 1 molar to 1 molar ratio. Okay, so the concentrations there um, the proportion of the concentrations is the same as the proportion of the moles. Okay, hopefully that makes sense. So here's some data for that particular reaction. Okay, and again, notice the way that it's measured here. It's the C4H9Cl. If you notice over here, okay, that's one of our reactants. So like I said, most of the time when we're measuring rate, we're measuring the disappearance of the reactant. And as you notice, if we start out with 0.1 molar here, and then that concentration slowly decreases until eventually we get down to 0. Okay. And then notice the average rate here is measured in concentration per second, molarity per second, instead of moles per second. Okay, so we can calculate the average rate here in terms of the disappearance of the C4H9Cl. And you can write the units two different ways, moles per liter times second, or just molar over seconds. That's probably easier, the second way. Average rate decreases with time, and that's what we were talking about before. As the concentration of the reactant decreases, it kind of makes sense that would slow down the reaction because now there's less of the reactant to come into contact with anything that it can react with here. Okay, and so we can actually do a plot here. We can do a graph of the C4H9Cl versus time. Okay, and because the rate changes, we can talk about instantaneous rate as well. And the rate at one instant might be different than the rate at a different instant as this reaction proceeds. So instantaneous rate, you need to understand that's different from average rate. Okay. Usually the instantaneous rate, we're calling that the rate of the reaction. We don't usually deal with solving for average rate here. Okay, so they're usually going to ask you at a specific time, what is the instantaneous rate here? So for example here, the instantaneous rate at time 0, the initial rate, yeah, that would be very hard to actually calculate unless you use this tangent, the slope of the tangent line, okay? And the slope of this tangent line, this dotted line right here that they have drawn, that is actually going to tell you your instantaneous rate at any given point, okay? And so we can kind of, I think the next thing that it asks us to do here is, using the previous graph, calculate the instantaneous rate of disappearance at t equals 0, okay? So what we've got over here, notice this is molarity, and this is seconds, okay? So if we take this tangent line, we find the slope of that, the rise over the run. Remember, slope is rise over run, or change in x, change in y over change in x, okay? And so if we can figure out a couple of points on this tangent line, then we should be able to figure out the rate here. Let's see. Let's pick a couple points that are fairly easy. There aren't any really easy points here. We'll go with a point maybe right here on this line, and then maybe we can use this point right here, because that seems to be pretty much on the tangent line. Okay, so I'm going to have to estimate a little bit here, but I'm going to say that, move this so you can see it. I'm going to say that our two y values here are probably 0.090. Well, they are 0.090 and 0.070. Okay, and so if we come over to the next, I'm being a little lazy with my units there. Those are both in molarity. And then next thing here, we've got our time is at about 50 seconds. If you trace this down, I would say it's about 50. And then our time on this one, probably a little bit more than half, so I'm going to estimate maybe 160. So our time here, 160, is that seconds? Yeah, seconds. 160 seconds minus 50 seconds. And I can use that to figure out the rate of this reaction. the instantaneous rate at time 0, which is, honestly, that's probably when the reaction is going to be reacting the quickest. So I'm getting a rate of 1.82 times 10 to the negative 4th molar per second. Okay, so there's my rate. For the reaction, okay, so now this one, this one's fairly easy. What were they asking us for here? Yeah, they were asking for the rate of disappearance, so that's fine. Okay. Now this works out pretty well when the stoichiometry is 1-to-1. Okay. Now where it gets a little bit tricky is when the stoichiometry is not 1-to-1. Okay. And most of the examples that they'll give you, it is 1-to-1. But we have a formula for this. Okay. If you've got coefficients in front of the equation, that actually does change the rate a little bit. And so you can figure out the rate of each of the reactants here. There's a lot of dashes and stuff here. This is a negative sign, this is a negative sign, okay? And the reason for that is because we're talking about the two reactants here, right? So they are disappearing. And then notice there are no negative signs on the C and the D, because those are the products, those are the ones that are being formed. And so if you can find the rate any one of these 4 ways, okay? These are all equivalent expressions to one another. The rate equals this, the rate also equals this, the rate also equals this, also equals this. Just depends on which one you want to use to figure it out. But it turns out what you have to do here is you have to, whatever your rate is, you have to divide it by the coefficient in front of the equation, okay? And so if you have a 2 here in front of this A, then you'd have to, multiply your rate by 1/2 or divide it by 2. Okay, and so that's how you take into account the stoichiometry that's going on in the equation. I don't want to talk a whole lot about that because I don't think that comes up a lot, and we've got other things we need to do here. So, but we will do one problem that maybe talks about that. Okay, how is the rate of disappearance of ozone related to the rate of appearance of oxygen in the following equation? We've got 2O3 gas going to 3O2, okay? So, basically what they're asking for is for us to write rate expressions for these two things. So I could say, okay, the rate equals, on this first one here, it equals 1/2 times the, if I'm writing it with respect to the O3, this is disappearing, so that's got to be a negative, okay? And then it's got a coefficient 2. We're going to put 1/2 here, okay? And then we're going to multiply that by the change in the concentration of the O3. Over the change in time, okay? And that would be equal to, let's see, the O2 here, it's going to be positive 1/3. Okay, and then we would multiply that by the change in the O2 concentration over the change in time. Okay, and so, I mean, we're basically just making that look like it looked over here. Okay, and so that's how those two are related to one another. So what you could say there is essentially the rate of the disappearance of the O3 is a little bit slower than the rate of appearance of the O2. And that kind of makes sense because there's more oxygens in O3. So, if 2 of the O3 molecules disappear, then we're going to have 3 O2 molecules appearing because that's how many oxygens we have there, okay? So the rate, this rate is a little bit slower. This rate's a little bit faster. Hopefully that makes sense. Okay? If the rate of the appearance of the O2 is 6.0 times 10 to the negative 5th at a particular instant, what's the value of the rate of disappearance of the O3 at this same time? Okay. So, if our rate here is going to be, let's see, 6.0 times 10 to the negative fifth meters per second, so 6.0 times 10 to the negative fifth, sorry, not meters per second, molar per second, is equal to 1/2, negative 1/2 times the change in O3 over the change in time. Okay, so they're wanting to know what's the value of the rate of, oh wait a second, I'm sorry, I messed that up. They're telling us the rate of the appearance of the O2, so that's going to be the 1/3. This is O2, not O3. Okay, so there's our rate for that. Okay, and then our rate for the O3 again is 1/2. Okay, so essentially, the difference between these two, the O3 is going to disappear at 2/3 the rate of the O2. And again, hopefully that makes sense. It's because of these coefficients in front of the equation here. Okay, so the O3 is going to disappear 2/3 as fast as the O2. All right. So if this is our rate for the and that's probably an easier way to think about this than actually thinking about the rate equations here. Okay, so if this is our rate for the O2, then we would need to multiply that by 2/3, and that's going to give us our rate for the O3, which should be a little bit slower. Okay, so 6 times 10 to the negative fifth times 2/3 should give us 4.0 times 10 to the negative fifth. I should have been able to do that in my head. Molar per second. Okay. Alright, now I don't anticipate you being asked a question like that on the AP exam. It's just an interesting thinking question for the rate stuff. Okay. Now we need to talk about concentration rate. And this is really getting into the stuff that you might see on the AP exam. And I'm going to have to move through this fairly quickly to make sure we get done in time. I get done in time so I can teach my next class. But in general, rates are going to go up as concentration goes up. We talked about that in class today. So you increase the concentration, that's going to increase the rate, okay? Because if there's more of the particles there to hit one another, to come into contact with one another, then they're going to react quicker. So that makes sense. Hopefully that makes sense. So we've got this reaction here, the NH4 plus, the ammonium ion is reacting with the nitrite ion to make nitrogen gas and water. And so what you have to note here is that as an NH4 plus concentration doubles, and the NO2 minus concentration stays constant, then the rate doubles. As the NO2 minus doubles, then the rate also doubles. Okay? And so we can conclude that this rate law here, the rate is proportional to the NH4 plus times the NO2 minus. Okay, now I'm going to try to hammer this point home a lot. I know it's weird because we just talked about stoichiometry and how to figure out a rate. But if you're coming up with the rate law for these things, really the only way to know how changing the concentration changes the rate of the reaction is to basically do an experiment. Okay, that's really the only way to know how to do this. So notice what they're doing here in this particular experiment. They're saying, okay, we know that rate generally increases as concentration increases. So we're going to start out with an initial concentration here of 0.01 for the NH4 and 0.2 for the NO2 minus. And then in our second experiment, we're going to double the concentration of the going to double our concentration of the NH4, but we're going to leave the NO2 minus concentration the same, okay? So this is still what it was before. So the only thing we changed is we doubled the ammonium concentration, okay? Now look what happened to the rate. The rate actually doubled, okay? So you double the concentration of the NH4 plus, you double the rate, okay? That's a good thing to know. Now look what they did, and they actually did that in a couple... well, no, I guess they didn't double it in the next two. so that's not really useful to look at. It could help you because it, increases by 3/2 or whatever, and so does the rate. So it looks like whatever the concentration of the ammonium is doing, the rate is doing the same thing. But another place where it's useful to look, notice on experiment this is 5 and 6 here, okay, we're doing nothing to the ammonium on these, but now we're doubling the concentration of the NO2. And notice what happens there. It goes from 10.8 to 21.6, which is also increasing by a factor of 2. It's kind of nice of them to write the scientific notation that way so you can see a little more easily that it doubles. Okay, and so we double the concentration of the NO2, we double the rate of the reaction. Okay, and so these things have to be determined experimentally to figure out exactly how the rate is affected by each of the concentrations here. All right, and so then what we're going to conclude here is we're going to write a rate law. Okay. Now, a rate law is basically just putting the concentration of both of your reactants, because again, remember I said that usually these rates are determined by the rate of the disappearance of the reactants, okay? So if you multiply the concentration of the NH4 by the concentration of the NO2 minus, and you also have something in there called the K, which is the rate constant, then that's going to give you your rate at any given time, okay? And so the thing that you can't see very clearly on this is that there's actually an understood exponent 1 on both of these, okay? When there's an exponent 1 there, what that means is that the concentration is directly related to the rate, okay? So if you double the concentration, you double the rate for each of those different species there, okay? Get into this a little bit more. So, whoops. So if we wanted to calculate the rate constant using the formula that we just had here, okay, the rate equals K times the NH4 plus times the NO2 minus. Okay, we know everything except the K here. If we look back at this data, now you can pick any set of any experiment that you want to figure this out, okay? Because they should all give you the same K because K is a constant, right? So that shouldn't change throughout the course of the experiments. So let's just use experiment 1. Okay, it doesn't really matter. You can use any of these, and like I said, they should give you the same K. But experiment 1, we've got an NH4 plus concentration of 0.01. Okay, so 0.01 times the NO2 concentration here, which is 0.2. Okay, and again, these are both in molarity. I should pay attention to my units here. Molarity and molarity, okay? And then in this first reaction, the rate here at those concentration ends up being 5.4 times 10 to the negative 7th. And that's molar per second, okay? Oops, I forgot the number already. 5.4 times 10 to the negative 7th. So that goes over here. 5.4 times 10 to the negative 7th. I keep not giving myself room for the units here. Molarity per second, okay? So then, we want to calculate our K here, our rate constant. And so we're going to, I'll just rewrite this for a second so you can see what's happening with the units here. Equals K times, if I multiply the 0.01, I should be able to do this in my head. 0.002, that's pretty sad. 0.002, and this is going to be molarity squared now, okay, because we're multiplying molarity times molarity. And then we're going to divide both sides. To solve for K here, we're going to divide both sides by the stuff attached to the K. Okay, so then we just kind of have to think about our units here. So you take the 5.4 times 10 to the negative 7th divided by 0.002, which should give you 2.7. Our K here is 2.7 times 10 to the negative 4th. And our units, we have to be a little bit careful here, okay? Molarity cancels out with one of these, so we're left with 1 over molar, 1 over second, okay? So probably the best way to write that would be molarity to the -1 seconds to the -1, which is kind of an awkward unit, but um, for whatever reason, the AP exam makes a really big deal about units on this particular section. With kinetics, a lot of times they'll say, what's the K? And they'll give you 1 point for the right number, and they'll give you 1 point for the correct unit. So you got to make sure you get that right. Okay, so just pay attention to your units in this particular section. Then we can use the rate constant to calculate the rate for any set of concentrations that we might pick. Now, is there a specific one that I gave you on here? I did not. Okay, so let's say that we just pick a set of concentrations here that's not on our chart. Okay, let's say we want to know if we've got the same concentration of NH4 and NO2, if we got 0.01 of both of those. Okay, so now we just, our rate, again, our rate law is K times the NH4 plus concentration times the NO2 minus concentration. And we just figured out that our K is going to be 2.7 times 10 to the -4th. Molarity to the -1, seconds to the -1. And multiply that by these two concentrations, which I said, I think I was going to try 0.01 for both of them. Doesn't really matter, I'm just sort of arbitrarily picking concentrations here because I want to see what the rate is at those concentrations. Okay, so then we multiply all that together, and that should give us our rate at this particular set of conditions. 2.7 times 10 to the -8th. And our units here, molar to the -1 cancels with one of the molars, and then we end up with molarity per second, which is a good unit to have for a rate. Okay, so that's kind of how that all works. Okay, so for a general reaction with the rate law, rate equals K times the reactant to the M power times the second reactant to the N power. We're going to say it's mth order and nth order. Okay, so in other words, if this is a 2 here and this is a 3, then I'd say this is second order, with respect to reactant 1, and third order with respect to reactant 2. That's how the terminology you'd use there. Okay, and then if you want to know the overall order of the reaction, you just add the exponents together. Okay, so this reaction, using my example, would be 5th order overall. Okay, and a reaction can be 0th order. Okay, that can happen. If both of these exponents are 0, then that actually means the concentration of the reactant does not affect the rate of the reaction at all. Okay, so it doesn't matter what the concentration of the reactant is. That's a 0 order reaction, so that can happen. And again, I'm just going to stress this a lot. The only way you can figure out these numbers right here is by experiments. Okay, that's the only way you can figure it out. Don't try to use the stoichiometry in a chemical equation. Okay, that's not going to give it to you. You have to know the reaction data. So anytime they give you a question like this on an AP exam, they're going to give you a set of data that you have to work with. Okay, I promise. Alright, so let's do some sample problems here. Reaction A plus B yields C. And the rate, they're giving us the rate law for this, or the rate expression. Okay, sometimes it's said rate law, sometimes it's called the rate expression. K times A times B squared. Okay. Each of the following boxes represents a reaction mixture in which A is shown as red spheres and B as blue ones. And again, that doesn't show up on your notes, so sorry about that. Rate these mixtures in order of increasing rate of reaction. Okay, so let's just assume each of these represents a mole per liter or something like that. Let's say that we've got this in a liter. If each of these boxes is a liter, it doesn't really matter because as long as we do it the same across the board. So then every dot we'll just count as 1, and we'll plug that into our rate law. Okay, and so this first one here, our rate is going to equal whatever K is, and it doesn't really matter because it's going to be the same for each of these. In the first one, A is shown as red spheres, so that's 1, 2, 3, 4, 5 of those. So k times 5 times b squared. 1, 2, 3, 4, 5. So times 5 squared. Okay. So our rate on this first one equals 125k. 125 times k. All right. On the second one, our rate would equal k times. This time we have 1, 2, 3, 4, 5, 6, 7 red spheres and 1, 2, 3 blue ones, and that gets squared. So then our rate is going to be 3 squared is 9 times 7 is 63, 63k. And then this last one here, the rate equals 3 3 A's and 1, 2, 3, 4, 5, 6, 7 B's. If I'm counting these right, they should add up to 10. So 7 squared is 49, and then 49 times 3 is 147. So this rate is going to equal 147k. So you can probably see how to rank these at this point. This is going to be the fastest rate in order of increasing rate. Okay, so it's a confusing way to say that. But the first one would be 63k, and then number 2, the second fastest, would be the 125, and the third fastest, the fastest one would be the one with 147k. Alright, if the concentration of both the reactants in the previous problem are doubled, what happens to the overall rate of the reaction? Okay, so we double both the concentrations. Let's look back at our rate law here, okay? So here's our rate law. Let's say we double both of those concentrations, okay? And we just kind of have to think about this for a second. So we double this concentration, the rate doubles, right? That's what it means to be a first-order reaction. If you double the concentration, that's what the rate does, okay? Now, if it's a second-order reaction, and we haven't really talked about this yet, but it kind of makes sense. If we double this one, then actually that's going to quadruple the reaction rate, right? And then we're multiplying these two together. So overall, that's going to increase the reaction rate by a factor of 8, okay? So it's going to increase by a factor of 8. And if you just kind of look at the expression, hopefully that makes sense to you. You double something and then square it, then you're going to quadruple it. And then you multiply it by something that's been doubled, then that's a factor of 8. Okay? What if the rate for this reaction was rate equals k times a times b instead? So there's no squared here now. It's just first order for a and b. Rank the mixtures again in order of increasing rate. Okay, so now rate of this first one equals 5 times 5 times k. So our rate would equal 25k. The rate on the second one would equal, what is that, 7 times 3 times k. So that's going to equal 21k. And then this one, the rate would equal 3 times 7 times k, which also equals 21k. So these two would be equal to one another, the second one and the third one. And then the first one would actually be the faster of the 3 rates. Okay, so this would be, these would tie for 1, and then this would be the number 2. Okay, overall reaction orders for the reactions described in the following equations. The overall reaction orders. So here's our first reaction here, and the rate is k times N2O5. Now, again, I'm going to really stress this. Notice there's a 2 here, coefficient. That does not mean this is squared, okay? That is wrong. The only way to figure out the exponent that goes right here is to do an experiment and see how the rate changes based on how you change the concentration, okay? So don't look at the stoichiometry to try and figure out your rate law. It won't work, okay? Except for in one case we're going to talk about later, but for now, it won't work, okay? So what that means then is the rate here is first order, okay? We just want the overall reaction orders here, which means we're going to add the exponents together, okay? So this is a first order reaction. Okay, now the second one here, the rate is equal to K times CHCl3 times Cl2 to the 1/2, okay? That's a little weird. That can happen sometimes. So this is 1.5 order overall, because we're just adding the two exponents together. This is a 1 plus the 1/2. Okay? What are the usual units of the rate constant for the rate law for the first equation above? Okay. So for the first equation, when we've got a rate order of 1. Okay? So if we think about our rate, usually it's molarity per second. Okay? Molarity per second equals whatever our K is times, and then this concentration here is going to be, the units are going to be in molarity. We're just thinking about the units right now. Okay? So if I solve for K here, divide both of these by the molarity, then my K is going to equal, notice these cancel out, seconds to the -1. That's going to be my unit for K for a first order reaction. Okay? Alright, using initial rates to determine rate laws. So reaction is, I think we're still, where are we? Okay, yeah. So reaction is zero order if the change in the concentration doesn't do anything, and I already sort of talked about that. The reaction is first order if doubling the concentration makes the rate double. It's nth order if doubling the concentration causes a 2 to the n increase. Okay, so you could put any number in there. It's second order if it causes a 2 to the second increase, or quadruples it. It's third order if it increases it by a factor of 8. Okay, 2 times 2 times 2 is 8. So that's how you figure out something higher than a first order. Now, usually we're going to talk about zero order, first order, and second order reactions. Okay, that's typically the ones we talk about. And then note that the rate constant does not depend on the concentration. Okay, the rate constant doesn't depend on the concentration. The rate does depend on the concentration. So I want to make sure we understand the difference between those two. Okay, the rate constant, which is the little k, doesn't depend on concentration, but the rate definitely does. Okay, sample problem here. Initial rate of a reaction A plus B goes to C is measured for several different starting concentrations, and here are the results. Okay, so we've got this experiment. Now notice, this is set up very similar to the one that we looked at before, where in the first and second reaction, concentration of A is kept the same. Okay, now notice A and B here are reactants, so those are the ones we're looking at. Reactant B is doubled. And look what happens to the reaction rate. Nothing. It doesn't change. Okay? So you change the concentration of B, doesn't change the rate of the reaction. So this is zero order with respect to B. Okay? Now, in the second and third experiment, we go from point 1 to point 2. And, well, actually, the best ones to look at here would be 1 and 3. Okay, so from 1 to 3, we double the concentration of A, but we don't do anything for B. Okay, and notice what happens here. This actually quadruples. Okay, so that means that our A here is second order. Okay, so we want to write the rate law for that reaction. So the rate here is going to equal K times A squared, because it's second order. And then I don't have to put B in my rate law at all, because B is zero order. It doesn't affect the rate of the reaction. Okay, so that's my rate law for this reaction. I'm going to have to cut this off here, and then I will... Let's see what I'm going to do here. We've just got a little bit left, so I'll finish this video as a second video for you to watch tonight, and I'll make sure and tell everyone in class. There should only be about 5 minutes left. So, okay.